Hello, everyone, and welcome to the next event in our webinar series. Today we have a talk titled Processing Soft Glass Optical Fibers. My name is Dave Gardner. I'm a manufacturing engineer for fluoride fibers here at Thorlabs, and I'll be moderating the talk today. Today's talk will be presented by Thorlabs application engineer Tyler Frisch. Tyler joined Thorlabs tech support team in 2013, at first assisting customers across the full breadth of our catalog. In 2018, he narrowed his focus as an application engineer, now dedicated to glass processing and inspection within our Vitran division. His main focus today is applications development for fluoride fibers and other customer-supplied fibers. Throughout Tyler's talk, please feel free to submit any questions you have using the Q&A tool, and we'll get to answering some of those questions at the end of the talk. And now I'll hand it off to Tyler for today's talk.
Thank you, Dave. While I am going to try to give an abridged background necessary for the talk, I do want to point out that Dave has a wonderful webinar on fluoride fibers linked below, so be sure to check that out later. There are a lot of mistakes to be made working with soft glass, and I'm sure there are many more we can discover together, so let's dive in. First, I want to start with an introduction. What is soft glass? How is that different from standard silica fibers you might be used to working with? And then what applications are using soft glass? What is the stuff even good for? Then jumping into some processing goals, what can we expect when working with soft glass? And what are some of the key parameters that present challenges? How can we address specific challenges that arise from material properties? Then I'll have a demonstration of some of the current techniques we use to overcome those challenges. For IT reasons, those are going to be pre-recorded, but I would be happy to show you in person if anyone wants to visit me in New Jersey. And then I'll get into what's on the horizon. What do we have planned at Thorlabs Vitran for soft glass handling and processing, and what do you need? So first of all, an introduction. Soft glass is an umbrella term that covers fluorides, chalcogenides, heavy metal oxides, really anything that isn't silica. You can't talk about fiber without starting with silica. It's been kind of the backbone of the fiber industry for decades. Most of the examples that I have today are going to be based around Z-blan or fluoroindate, just because that's what the Thorlabs manufacturing team is working with. But silica is easy to draw. It's abundant and inexpensive. It's a mineral, SiO2, and billions of dollars has been spent over the years to get the purity of that down to parts per trillion. By contrast, fluorides are a mixture of chemicals, so the what you get is not a direct measure of purity. Silica, though, is also limited to the near infrared. You can actually make a decent case that the line between the near infrared and mid infrared is where silica stops being an effective transmitter. So for applications, many of those are going to be soft glasses utilized for mid-infrared applications where it transmits better than silica can. Why move into fiber? Well, for one, scale and stability, fiber is preferred over free space whenever you can. But this affects fields like spectroscopy with chemical sensing and fingerprinting, environmental or meteorological sensing, mid-infrared imaging, whether that's with coherent bundles or optical coherence tomography. Fiber lasers are a common application, both surgical and materials processing, but it's really these last two that are near and dear to my heart. Supercontinuum generation and telecommunications. These are the reason that I at Vitran started getting involved with soft glass and fluoride splicing. So for supercontinuum, Thorlabs laser division offers two supercontinuum sources, the Prism award-winning SC4500 and the newly released long-wave IR supercontinuum source out to 11 microns. Those are both linked below. And those both use an indium fluoride fiber to utilize some of the nonlinear effects there. And then in telecommunications, this is actually not a mid-infrared application, but an O-band telecommunications wavelength. There's a PDFA, praseodymium doped fiber amplifier, and that uses a process that actually can't be done in silica, but can produce high amplification with low noise introduction. So I think that is also listed below. But just because these types of fibers are under development and constant improvement doesn't mean that we don't already have reliable performance that is available on the market. As for what the processing goals are, it's easy to say that you would like everything to work exactly like silica does. Unfortunately, it doesn't. Otherwise, I wouldn't be here and you wouldn't be watching. So I'm going to split these goals into two separate categories. First is the handling or mechanical properties, and second is the processing or thermal goals. So for handling, that's going to be how to prepare the fibers for processing, stripping off the coating, cleaning away any residue, and then getting a good cleaved end face. And then processing is going to be splicing and tapering. Those are really the building blocks to make anything out of fiber. So what do I mean by splicing? Hopefully this is playing on the media viewer. Maybe it is now. But splicing is the process by which you join two fibers end to end. So typically what that entails is bringing the fibers together, applying some heat, and then moving one into the other so that the glass flows and a joint is formed. For silica fibers, that's pretty straightforward. And for many soft glasses, splicing the soft glass to itself is straightforward. You also are going to want to splice soft to silica on occasion. And so we'll have some other goals there as well. The other processing goal is tapering. I have another animation here. The blue is still glass, but it's just much easier to see a tapered shape this way. Tapering is a process of heating the glass and then elongating it, and that reduces the diameter. So that's critical for mode field adapters as well as fused fiber couplers. There's two ways to do it. Either you draw the fiber out on one side and feed in on the other, or you can draw on both sides. That's called a biconic taper, and that's very useful for mode field adapters and for fused fiber couplers and side pumps. Both of those processes need to be low loss, although I'm not going to talk a whole lot about loss today, mostly because I want your help with how to measure loss. There's a few challenges there. First of all, soft glasses tend to have a higher attenuation component, just intrinsic to the fiber, so it's a little difficult to differentiate your splice loss from your attenuation in the segment that you've spliced into. And second is that you get different mode mismatches, particularly when going from silica into these soft glass fibers that are designed for mid-infrared performance. So first of all, to differentiate the attenuation from the splice loss, you can always do a cutback. So after the splice, you cut off that section of fiber that you just spliced on and leave only a few millimeters or a few centimeters so that you can look at just a piece that has a minimal attenuation just from having a minimal length, and then directly measure your splice loss. The problem with that is you've just destroyed the device you made. And if you're using a soft glass fiber that costs hundreds of dollars per meter, then doing many cutbacks to develop a splice process can start to get very expensive compared to in silica, where you're dealing with things that are more like $1 per meter. So as far as the mode mismatch, I want to know what kind of metrics you would be interested in. And the way I see it, there's 5 obvious choices. One, something that's available today. So a 1550 or 1310, even a visible stabilized source. These exist already. You might even have one in your lab. And even though it might not be ideal for the splices that we're talking about, it's available and that's what counts. Then a new mid-infrared standard might be needed. I know that there's a 2.7 micron mid-infrared source linked below. The 3.39 micron Heaney wavelength is available, if not common. Or quantum cascade lasers can be made at a broad range of wavelengths. Is it just that we need to pick one of those and define the loss for some mid-infrared wavelength? then we could use a middle ground. 2 micron, at least for Z-blan, behaves pretty similarly in silica and Z-blan. That's not really true for indium fluoride or other soft glass fibers, and that similarity is really only in its attenuation. Or do you only care about your specific application, and as long as you can quantify it with the source you have, is that good enough? And then last, and maybe most expensive, is it broadband or bust? You need a full curve like this for the splice loss across every possible wavelength. So what do you need as a measurement tool? And I think if I advance this slide, you'll even be able to vote on a poll. So I'll leave this up just for a moment. I think once you submit, it will turn your screen dark for a moment, but it'll come back when I advance to the next slide. So how can we help quantify that to best suit your application in the future? And I'll move on now. The other processing goal, which is a lot easier to talk about, is strength. Typically, silica is going to have a breaking strength of 600 to 800 kpsi for the bare fiber, and that's proof tested to about 100 kpsi to weed out defects. Fluoride fibers, I think proof test is going to be closer to 40 kpsi, which comes out to about 350 grams if you're working with 125 micron diameter, which that's plenty to work with, plenty to handle. If you have a splice strength that's even 50 grams, that can be unloaded and packaged. On the right, I have 5 images, and you can see how much difference of rounding there is of the Z-blan fiber on the left, and this is spliced to a silica 80 micron diameter on the right. So this is our IRZS23 single mode Z-blan, and up here the corners of that Z-blan are barely rounded, and at the bottom it's almost a bulb that forms the splice joint. So these 5 different splices are the same fiber. They only change is that the power was changed by 0.01 watts, 10 milliwatts per division. So this whole range is 40 milliwatts different, which is about 3% of the 1.4 watts splice power. The change in strength across these is incredible, though. On the cold and hot end, on the top and bottom here, these each had a splice strength of around 50 grams, whereas this middle one, the Goldilocks, had a splice strength of over 200 grams. So a lot easier to measure, a lot easier to set as a goal. So now that we have our goals addressed, what are the parameters and challenges that we're going to get with soft glass? Again, we can split those into 2 main categories: the handling or mechanical characteristics, and then the processing or thermal challenges. There will be a bit of overlap between these 2, but let's jump in with mechanical curl. So curl in a fiber means that the fiber might not be where you think it is. If you're holding it in some sort of micro manipulator, by the time it overhangs into your heat source, it can be off by quite a bit. So you really need to make sure that you have as little curl as possible, or overcome it by being able to move the fiber tip directly to the heat source. Curl comes from stress gradients, either in the coating or in the case of soft glasses, in the glass, and that's caused by thermal gradients as a part of the draw process at the manufacturer. This is something that is getting better, though. There's less curl in newer, more mature fiber draw techniques, but a lot of you are working, I think, with experimental fibers, one-off draws, and might not be optimizing for those mechanical properties as much as you are some specific optical property with the dopants in that fiber. So if the curl is in the coating, then it's pretty straightforward to remove with heat, either from a heat gun or a commercially available curl remover tool, which will have a channel that is heated. If you're working with soft glass, be careful with solutions like that. I know a heat gun, typically the heating element can get up to 650 degrees Celsius, which is way too hot for at least fluoride fibers and many other types of soft glass fibers. And then this next approach might not be directly relevant to everyone, but if you have just donated 14 inches of hair, a hair straightener operates around 200 degrees Celsius, and wrapped in some Kevlar sleeves, that actually is a pretty effective way to remove curl, at least in the coating. The last thing I want to say about curl is it can be overcome with the fiber handling and manipulation of whatever motorized process you're using to bring the fibers together. If you have both X and Y adjustment, then absolutely great. You can just move the fiber tip to where the heat zone is. If you do not, it is still possible to overcome it with eccentric alignment. So I think this is playing now. Those were straight fibers aligned to an axis of whatever heat source you have. So the left fiber there is able to move up and down, so it can move directly up to where the heat axis is. On the right, if that motor only moves front and back, then that's never going to get you any higher. But if you have a rotation axis, then you can rotate the tip of that fiber about some arc until it's in the same line that you have for your direction of movement for that. The next mechanical parameter I want to talk about is brittleness. Silica is famously brittle. That's why it cleaves so well. Soft glasses are even more brittle, which does present a few challenges. Again, this is something that is getting better as manufacturing processes improve. Fewer micro defects on the surface of the fiber as it's drawn means the strength can be greatly increased. But the best thing I can say is just keep a clean working environment. Don't have any tools or anything that the fiber can snag on, even on your workbench, and make sure that your workbench is dark. I just use a piece of foam board from a craft store, just black foam board, to really bring out the visibility of the fiber. Continuing on with brittleness, mechanical strip tools are not going to be ideal. When you strip a fiber using a mechanical tool, you'll mar the glass, and then you need to pull a tension to remove the coating, and that tension is actually going to be enough. The adhesion of the coating is going to be enough tension to propagate that flaw into a full break. So instead, it is highly recommended that you use a chemical stripping process, just having some chemical soak to soften that fiber coating, and then use a soft tip strip tool like the FSGT, which is linked below, to pinch and break the coating without marring the glass surface. There are a number of conformal coating gels available on the market, as well as hardware store paint remover actually works pretty well for some applications. It depends on what the coating composition is. I will say, make sure that you're using a chemical that is appropriate for the glass type you're using. For example, fluoride glass is attacked by acetone, so don't use an acetone-based strip chemical for fluoride, at least. Dichloromethane is pretty common as well, and actually that dissolves most coatings pretty quickly. Soak time could be as little as 30 seconds. One more thing, make sure anytime you're using a chemical strip to use proper personal protective equipment, wear gloves, have a well-ventilated area, and also let your lab safety officer know what chemicals you're bringing in. A lot of these chemicals are known to the state of California to be harmful, so always put safety first. The last thing I want to say about brittleness is in cleaving these soft glasses. I want to make sure this is playing again. I highly recommend using a tension and scribe method. So that is clamping both ends, pulling on one to apply some tension, and then bringing a blade forward to induce a flaw. And that flaw under tension is going to propagate very quickly into a flat cleave. There are several differences between doing this with silica and doing it with soft glasses. For one, you'll want to use a backstop. That can support the fiber on the back opposite the blade to make sure that the blade isn't just causing the fiber to flex. And the reason that it would be flexing is because the tension has to be much lower. So if you use the same tension that you would use with silica fibers, you'll get these marks from hackle. Typically, for silica fibers, you'll reduce the tension if you have a structured fiber like a photonic crystal fiber or PM fiber. And so backstop cleavers are already available, but the same is true for soft glasses. You'll often want to use a backstop in much lower tension. Another thing that the soft glass fiber manufacturers don't particularly like my recommendation on is humidity. Humidity can help the flaw propagate into a flat cleave. It can also be a nucleus for crystallization on some fibers. So make sure that you, if you introduce any humidity before you apply any heat, get rid of that humidity as well. If you want more information on fracture theory and cleaving optical fibers, Andrew Yablon has a very good book called Optical Fusion Fiber Splicing, and that's got a lot more information on that. On the right here, I do have an image of a fiber where I delayed adding any humidity, and I add that just by exhaling on it, just like breathing on glasses to clean them. And as you can see, this scribe mark is huge. I had to eventually breathe on it just to make sure that I didn't damage the blade. I mentioned earlier that tension and scribe is preferred. You might also be familiar with scribe and bend. Those are the small little mechanical cleavers, usually where you close a lid to clamp, slide a blade forward, and then press a button, which makes a spring bend the fiber to give the appropriate stress to break it. Those are really designed around silica fibers and don't work well for soft glass. This left image is my attempt at using one of those. And as you can see, I wouldn't consider this a cleaved surface at all. So if those existed for soft glass, I assume they would be very specific to the fiber that they're cleaving. Next, moving into processing parameters. Glass transition temperature is a range. So glass has a phase between liquid and solid. For silica, that range is around 1700 degrees Celsius, but it's a few hundred degrees wide. For soft glasses, what that range is varies a lot depending on what type of soft glass you're using. For fluorides, it's in the neighborhood of 300 degrees, but the width on that is only tens of degrees wide. So you have a much narrower working range to be in. And in addition to that, the slope by which you soften, by which the viscosity is reduced, is much steeper than it is with silica. So because of that, heating uniformity is key. It is critical for the fibers to be in the center of the heat zone. So like I showed earlier with that eccentric alignment, that is one way to make sure your fibers are where the heat is. You also need to make sure that that heat is evenly balanced between the left and right fiber. So here, let me begin this animation as well. So this is a heat source coming up, in this case a filament, that is going to apply some heat to cleaved fibers. The fiber is not pushed in any way. It's just that the tips are melted back and form a ball. And then you can look at the melt back distance that each of those moved, as well as the diameter of that ball, to determine whether your heat needs to be a little more towards the left or towards the right. So I actually have some real images of what balance looks like. This is using a GPX 3900. Now that you have uniformity, heating precision is key. So these are balance images that show the amount of heat on two fibers. All of these fiber pairs are IRZS23. That's the same single mode Z-bland fiber. And this is a comparison of on the right standard power mode versus, I'm sorry, on the left standard power mode versus on the right our low power mode. So standard is just what we used to use with silica that had a resolution of 1/10 of a watt. And as you can see, there's a huge difference between 1.3, 1.4, and 1.5 watts. Here up at the top, 1.3 watts is so cold you can't really get any information out of that. And on the bottom, 1.5 watts is so hot that the fibers are melted basically off the screen. So really it's a Goldilocks, and hopefully 1.4 works well for this application. But if you have a much higher heating resolution, you can get a much better gradient. You can tune the amount of heating that you're actually imparting onto the fibers. I do know that other heating systems, CO2 and arc, have calibration methods as well. I'm not entirely familiar how those work, especially at these temperature ranges. I think with CO2, it's easier to adjust the duty cycle of a scanning beam than it is to directly alter the power. But I've got a bias towards filament, both because it's what I have and because filament is what's used in draw towers. It's a very mature technology, so it's easy to adapt from that into processing. So once you have the uniformity and precision, now the accuracy is key. These are those same 5 splice images from earlier. Again, silica is never going to melt at 300 degrees Celsius. So what this splice method is utilizing is basically biasing the heat towards the silica, heating it up like a brand, and then pressing it into the Z-bland fiber, in this case, a larger diameter Z-bland. And then embedding that silica in the Z-bland forms a joint with hoop stress as it cools. Again, each of these is different by only 0.01 watts of heating, but there's a huge difference on rounding and a huge difference on strength. Soft glass is a less mature technology, so it is under constant improvement, and in many ways that is good. In some ways that is a challenge. So for example, I repeated that experiment with a different spool of IRZS from a different lot that I got much later, and plotted the same strength. I found the ideal splice power was much lower, about 1/10 of a watt lower. And the only difference there is just it was a different lot. I used the same glass processing system with the same type of filament. I even balanced both systems to have a similar heating effect, both in the melt back of the ball as well as the diameter of the ball on both sides. So there is just difference in one lot to another on what strength you can expect. So it is always best at this point to balance using the fiber you're about to splice. There is not yet a gold standard fiber like there is with silica. For example, SMF28 from Corning is a silica fiber that is so reliable you can set your watch to it. Until we have something like that with soft glasses, you're always going to want to be balancing and tuning your splice parameters with the fibers that you have on hand, the lot that you have on hand. And getting a standard is going to be much more difficult just because soft glasses are not a mineral of definite composition. It's not SiO2 that you can just increase the purity to get better consistency. So now on to demonstration. I'm going to start this video off right away. Again, always use personal protective equipment. What I have here is an indium fluoride fiber. This is a multi-mode 100 micron core, 190 micron cladding diameter. And the soak that I've used is a conformal coating strip gel. I have about 0.7 milliliters just drawn into a syringe. That 0.7 is just to give me the length of strip that I desired. And This coating, I think, soaked for about 2 minutes before this. But there I just pinched the coating and removed it without damaging the glass underneath. Fortunately, the cleaning is very similar to silica fibers. You're just going to use a solvent-soaked wipe. Again, make sure you choose an appropriate solvent for fluoride. That might be methanol, but whatever is appropriate for the soft glass type you are using. And you're just going to pinch and wipe and even rotate the fiber to make sure you clean all around. Next is the cleave. And I want to make sure that this is actually playing. So again, this is that same fiber, 190 micron indium fluoride. The tension I'm using is 170 grams. I've actually removed some of the magnets in the lid to decrease the clamping force because it wasn't necessary. You see on the left, I just clamped the fiber, and on the right, I'm lifting the stripped end out and allowing the vacuum to draw it back in, and then closing the lid and engaging the cam. The blade just moved forward there, so it's going to take several pecks, and in a moment I'm going to exhale onto the fiber to just introduce that humidity. This is a case where the backstop could have been helpful. It is not in this video employed, but certainly would be helpful for achieving a high cleave quality. Again, if you are going to increase or introduce that humidity, make sure to remove H2O before you apply heat. And that can be done just drying out over time, or if you have some solvent you can use to ultrasonically clean it away. Next is balance. So this should be popping up as well. Once you have two cleaved fibers, you can use them to balance the heat source. I have a screen capture of two fibers there. On the right, you'll see that fiber is about to be moving. And if you look in the picture-in-picture, it's because that the fiber holding block is rotating. This is that eccentric alignment we saw an animation of earlier. And now the camera's switching views to look at a perpendicular view to do the same thing for the left fiber. You'll see that left block is rotating, so on screen, the left fiber is rotating. Once those are aligned to one another, then you can bring the camera away safely so that your heat source can be moved over and up. The heat source in this case is an iridium filament, specifically size V3. I think if you're looking for that, it should be on the GPX 3900 page below. Again, that heating uniformity is critical, so eccentric alignment has to be done anytime you're heating, at least with this system. And iridium is going to have a longer lifetime than either tungsten or graphite. Usually iridium is good until you break it, either by accidentally putting in too much power or heating up the glass so much that you drip glass onto the filament. And because there is no standard calibration fiber, this balance is being done with the 190 micron clad indium fluoride fiber that I will be splicing later. So here you can see there's about 128 micron melt back on either side, and it is pretty close to even within a micron. Okay, the next video that's going to play is for the splice and the taper. This is going to be a draw taper as opposed to a biconic taper. So the first thing that happens is a splice. This is a fluoride to fluoride splice, so I'm not using that silica brand method. This is just going to be a direct heating, radiative heating of about 6.5 watts. Still the 190 micron clad indium fluoride fiber. I skipped the eccentric alignment in the video, although that does always have to be done. You need to make sure you're well centered on your heat source. So the camera is moved away so that the heat source can move over and up. If you take a look down here at the tension monitor, you can see as soon as the splice is over and starts to cool, there is some tension that is pulled, and that's just the coefficient of thermal expansion, or contraction in this case, that after the splice joint is formed, those are cooling off and pulling a little bit, which is good, especially if we're about to do a taper. So a taper, usually you're going to start with a little bit of tension on the fiber, but now you can see the camera is moving out of the way. I'm targeting a taper ratio of 5:1, so that 190 micron clad fiber is going to be tapered down to about 40 microns at the waist. So I'll start with a down taper over about 13 millimeters to get down to that 40 microns, and then I'll hold that waist for another 3 millimeters and then end pretty quickly with a 1 millimeter up taper, just so it all fits on screen and I can show it to you later. If you've done silica tapering, typically there's going to be some tension during that down taper and waist. Here with this splice file, the tension is really in the noise until the heat is finished, the taper is done, and you'll see the tension again, it cools off a little bit. So there's that up taper, and I'll scan over so you can see how smooth the taper is. And then I'll jump back over to the up taper just because it's a good place to talk about it. So again, 190 micron cladding down to 40 micron or so waist diameter. So now that that's splicing and tapering, really what's next on the horizon is component manufacture. Splicing and tapering are the building blocks for combiners, mode field adapters, lensed fibers. Biconic tapers are a little bit different, but those are used for couplers and side pumps. Another thing that I want to make sure that I'm able to do is specify loss in a way that's useful for you. So hopefully that poll worked well. And then your application is on the horizon. What are you having trouble with? And what tools can we offer in order to facilitate your soft glass processing applications? So with that, thanks to all of you for watching. Thanks to many people for helping make this webinar happen. And I'll turn it back over to Dave.
Thanks, Tyler. Thanks for all of that info. We did receive a few questions during the talk, and I'd certainly like to invite the group if you have more questions. We have some time for Q&A. So yeah, any other things you'd like us to discuss, please put them into the Q&A box now. To start with, we had a few questions, like I mentioned, that came in while we were talking. So the first, the question is, how do you measure the splice mechanical strength? So maybe we can go over that generally. And the question was also asking about the GPX. Do you have problems with the fibers slipping in the V grooves?
Yeah, so generally the tensions that you're measuring are not going to be enough to cause slipping. It depends on what coating material you're using and what diameter you have for the V grooves and the clamp. But if you're measuring up to a few hundred grams, slipping shouldn't be a problem. The GPX has a load cell, so basically a flexure and a strain gauge combination that's calibrated in-house before the unit ships, that as the fiber holding blocks pull, that flexure is moving and the resistance in the strain gauge is changing, so that gives you a direct tension measurement and you can see what the tension was when it breaks. There are other proof test methods or strength test methods that are similar. Some of them use a rotary drum. Usually you'll use a rotary system when you're trying to do much higher strength testing. So that 600 to 800 kpsi with silica, that would have to be done on a rotary system.
That's a lot.
Yeah.
Okay. So another question we had that came in, you showed us the eccentric alignment procedure for if the fibers have some curl.
Mhm.
Is that automated on any of the Vitran equipment, or is that a manual process?
We're about to release a update of the software that has the eccentric alignment automated. Um, I do have right now, I think you saw in the recordings I did, just notes prompts that I added for whether I'm in the left fiber view or the right fiber view, which one to be rotating. But that is something that will be automated very shortly. I think the next release should be coming out within a couple weeks.
Okay. And I guess the follow-up question for that, is there a limit to how much curl you can deal with? You can make go away in that process?
Yes. So whatever diameter the arc is uh, that fiber is tracing, and maybe I can jump back to that animation or the end of it. You need to have enough travel to compensate for that. So if you have a travel of say 1 millimeter and your fiber is curling 2 millimeters, there's not a whole lot that you can do with that method to move back to center, and really curl removal is going to be critical there.
Got it.
Yeah.
Okay. So a question, how consistent is the fiber splicing with respect to change in power? And I'm thinking that probably means filament power, which I think
Yeah.
you may have touched on some, but yeah, we can jump back to it.
Yeah. So the biggest change is going to be from one lot of fiber to another. If you're using the same type of fiber, the same lot on the same system with the same filament, you could do many splices in a row and achieve, did I actually jump back? There we go. And achieve the same quality splice. So you can see even just walking the power up how much this is a gradient. So there is repeatability there as long as you're maintaining as many of the conditions as you can. I have seen spools of fiber, particularly experimental, like one-off draws, where the thermal properties change down the length of the fiber. That's a little more difficult to dial in and correct for. You just have to count on, that change being slow, and monitor it both for power and the shape of the splice. One other note I want to make while we're talking about that is I'm not trying to claim that this amount of rounding on the 1.44 watt splice is ideal for all fiber types.
Hmm.
Even on the indium fluoride version of single mode that Thorlabs offers, I found the ideal power had a lot less rounding on the corners. It looked visibly more like this top image.
So if someone's going to do this, they're going to try a few different powers, characterize for strength, characterize for loss, and that's kind of how you figure out, yeah, rather than what the splice looks like.
Exactly.
Got it. And you said that, you see when you keep as many conditions as the same, you're going to get consistent performance. So that 1.44 watts, if you kept doing that same day, same fiber, we're going to see similar performance. With fiber lot changing, we know things can change a lot. How
Mm-hmm.
about if you come back the next day with the same fiber? Do we need to do balancing all over again? Do we need to change our ideal power, or is it pretty consistent?
I usually balance at the top of every day just because it is a mechanical system and you want to make sure that everything is in the same position. Um, I think your mechanical tolerances are going to be looser than the thermal or optical tolerances at that point. But it should be a very similar splice file from one day to the next with the same lot of fiber.
Got it. Okay. And actually, as we were answering that question, we had a follow-up come in. Very
Mm-hmm.
cool discussion. So the question is, could any changes in splice power be attributed to geometrical differences between different filaments? For instance, is it that instead of the fiber lots? So maybe if you want to take the filament part, and then I'll address the fiber lots part.
Yeah, so the two filaments will behave differently over even their lifetime, more so with graphite and tungsten than iridium. But the tolerances on the loop diameter for a filament, for example, are pretty tight, and I would expect two filaments to behave very similarly, especially once you're balancing if you're accounting for that thermal adjustment of power offset. Certainly, two graphite filaments are a filament that I expect to age and oxidize over time. That's going to be different, not just between two filaments, but between the same filament at a different point in its life. And that's another reason you want to make sure you balance and readjust for heating effect.
Understood. Yeah, and I guess just to comment a little bit on the fiber lots part of it, we're talking about tiny mechanical differences in filaments and mechanical alignment. I think all of that is a lot easier to make consistent compared to fluoride fibers from lot to lot. From the manufacturing side there, we can't use MCVD to make the glass, to make the fluoride glass. And some of the things we have to do make it harder to get the exact same glass composition from fiber lot to fiber lot. Unfortunately, fluoride glass also has an extraordinarily steep viscosity versus temperature curve when you're in that glass transition temperature. So you have a very small window to work with, and that's what this slide illustrates. The new lower power GPX splicer, we can get that extra digit of precision with how many watts we're putting into the filament. These fibers are also very low melting point, which means we're running that filament. It's like driving a sports car around on idle. It's going to be hard to control things. So, and yeah, we have call it like a 1 degree, 2 degrees C temperature window where the glass is going to be the right softness to perform a splice or a taper or whatever. And so when you couple that with, yeah, it's hard to make the fiber consistent. Obviously, Thorlabs, a big focus for our fluoride fiber is manufacturing consistency, but we live in the real world, it's hard. And then this glass is very sensitive to temperature changes. Yeah, in my opinion, that kind of swamps everything else in terms of, filament geometry and things like that. When you see, these differences from day to day. As Tyler said, there's no standard fiber. In the silica world, we have SMF28. It's always the same. Corning does a very, very good job at process control. And so you can basically calibrate the heat your system is putting into the fiber using that SMF28. For fluoride glass and other soft glasses, it's much more like you're gonna get your fiber lot and then figure out how much energy to put in to get the desired behavior, and that's your calibration point. Just my 2 cents. Okay, so a couple more questions. So let's see. Question, have we tried to fuse end caps onto soft glass fibers?
Yes, so one of the things that has been requested is like an end cap of either calcium fluoride or zinc selenide. I haven't fused either of those yet, but that would be a very similar process to what I'm doing with the silica, using that as a brand, and then forming a splice joint there, and then cleaving the end cap. Or if the end cap is already cut to size, then it's just an issue of holding that end cap in the heat source. So yeah, let's add that one to the on the horizon list as well. If you have a specific end cap that you're looking for, let us know.
Okay. Another question, have we seen, we're talking about these tiny variations in power that make the glass behave differently. Does the temperature of the room or humidity in the room matter? Is it that sensitive?
The temperature of the room, I don't think would matter. I mean, you're talking about a few hundred Celsius, and your room is going to be 25, 27, maybe up to 30 or 40 in extreme environments. I don't know many lab or production environments that are that poorly controlled for temperature. Humidity, I think probably could be a bigger issue. I know that at least with the GPX, we're purging that filament body with ultra high purity argon, so 99.999% argon, and the H2O content of that purge gas is very low. So I would hope that would displace any contribution of humidity in the room, but I have not made an attempt to do this outside in the summer. But perhaps I'll take a trip down to the Jersey Shore with a splicer and let you know in a couple months.
Okay. So we had a question, I think kind of getting at that picture where we showed the fluoride spliced into the silica. And the question is, we're looking at the different amount of rounding on the fluoride fiber. Is that due to pushing the silica into the fluoride, or is that also due to temperature that we see the difference in rounding over?
Yep, this is both. So the amount of push is the same in all 5 of these images. So the difference is due to the temperature change, and mostly that's going to be the temperature of that 80 micron silica on the right and how much heat is able to diffuse into the Z-blend target. But yes, so in this case, the push is the same. It is only the heat that is different. On these balance images, the Z-blend was held at a known position. These all started at the same position, maybe 50 microns between the 2 fibers. And then it is only the heat that is melting that back. There's no mechanical motor movements during the balance once that heat is applied.
Okay. And when you're doing the brand method, you're heating the silica, the small silica fiber, pushing it into the fluoride fiber, melts the fluoride fiber. Does the push force matter a lot? Is that a important parameter?
You do have control over the velocity of that push. I haven't played around too much with what that is, only to make sure that that push is happening in a timely fashion so that the silica doesn't cool off too much, but not so fast that I'm going to, impart some lateral stress or jump in the motor.
Okay, understood. So switching a little bit topics, I had a question. I think it's about the fiber stripping and the different materials used. The question is, are fume hoods needed for those materials, working with those materials?
It would depend greatly on the material. I don't use it in a fume hood. I've just got less than a milliliter in a syringe. It does evaporate over the course of the day. If you're using something commercially available from like a hardware store, those are typically used in greater quantities for the application of removing paint or something like that. It certainly couldn't hurt, but that's definitely one that I'm going to defer to your lab safety officer. So give them the material safety data sheet and let them make that call.
Yep. Okay. And our last question for now, unless any others come in, a little bit of a different topic. Can we comment, and I think I might have some info on this one as well. Can we comment on the techniques used in creating fiber Bragg gratings in soft fibers? Would you like me to take that one?
Yeah, if you can take that one, please do.
Yeah, so I think that's a little bit outside the GPX processing equipment, but there are some research groups that are trying to do Bragg gratings in fluoride fibers. Really, in general, the fluoride fiber world, we can manufacture these fibers, but we're missing some of the tools like couplers, FBGs, circulators that you would need to easily make an all-fiber device, things like fiber amplifiers and fiber lasers and things like that. So for FBGs, there are a few different methods, but mostly they're using UV light to modify the index of the fiber. There's some differences on exactly how you focus that light in, point by point, plane by plane, things like that, which I think is a little bit equivalent to how they're done in silica fiber, or the different approaches to them in silica fiber. This is something that Thorlabs has interest in, and we've seen some results that are promising. And it's a field that we really hope, we can see some more progress in the future, because we think it'll just enable more applications for fluoride fiber, which is kind of what we're all about. But yeah, typically we're using UV to create those index perturbations in the fiber that then is going to create the grating within the fiber. I'm not an expert in that field, so that's about as much as I can comment. Hopefully that answers the question. But yeah, definitely an interesting one. We hope to see more of in the future.
Yeah. I know there's a few other people on the applications team here at Thorlabs Vitran that have done more with Bragg gratings and long period Bragg gratings. So I don't have any expertise in that area, but certainly I'll reach out to them and see if we can get a more direct answer.
Yep. Yep. Okay. So that is going to be all the time we have for questions today. We'd like to thank everyone for joining us today for the webinar, and we hope you enjoyed it. I certainly thought it was interesting. Thanks, Tyler, for all of that informative presentation. And also, we'd like to let you know about our upcoming webinars. So our next webinar will be on June 12th, where a Thorlabs solutions engineer is going to discuss achieving long-term optical stability within your system. And additionally, and perhaps even more exciting, Monday, April 8th is the total solar eclipse we're going to have here in the United States, and we'll be live streaming that eclipse both from locations in Rochester, New York and Austin, Texas. And both of those locations will see the full total solar eclipse. We have 2 chances for no clouds. So we hope you'll join us for that as well. Both of these events, both of these webinars, you can register for them at thorlabs.com/webinars. Thank you very much again for your attendance and the great Q&A. And thank you again, Tyler. And we hope to see you all again soon. Thank you, everyone.
Thanks, Dave.